Okay, so we now have that, that the orbital radii for the electron are now quantized. They can only take on discrete values given by this relationship here, and uh, uh, traditionally we designate this collection of constants 4 pi epsilon naught h bar squared over m e squared. M is the mass of the electron, E is the charge of the electron. We give that collection of constants a name. We call it the Bohr radius, and we give the symbol a sub 0 or a naught. Okay, and so it should be obvious that we expect that this has units of distance, because n and z are both integers. N is just the principal quantum number, okay, and z is the atomic number of the nucleus. Okay, so let's actually find out what the actual numerical value of a naught is. Again, it should have units of length, so let's find its numerical value. Okay, and we can use a little trick. Okay, we can use something called the fine structure constant. This is an important constant of nature that appears in particle physics, and it's just a collection of other fundamental constants. Okay, and so the fine structure constant we call alpha, and it's equal to e squared over 4 pi epsilon naught times h bar c. Okay, these are all constants, and its value is about 1 over 137. And actually there's a lot of research that goes on actually trying to measure, put limits on that value to make it more and more precise. Here I'm just giving it to 3 significant figures, but it's known to many more than that. Okay, so with this we can rewrite a naught, so we can write the Bohr radius is equal to 4 pi epsilon h bar c over e squared times h bar over mec. So now I've actually I've explicitly written the subscript e on the mass of the electron, just to remind us that it's, for this particular part, that it's the electron mass, since that's what appears in the fine structure. Since that's what appears in the Bohr radius. Okay, and we recognize that this here is 1 over alpha, so it's about equal to 137. Okay, and this we can multiply top and bottom by c, so we can put a c on top and a c on the bottom, and now we have our happy h bar c, which we know the value of. Okay, and so this is approximately equal to 137 times h bar c over mec squared, and this h bar c here, this is equal to about 197 electron volts times nanometers. Okay, and this is the rest energy of an electron, which is about 511 kilo electron volts. Okay, so when you plug this all in, you get 137 times 197 eV times nanometers divided by 511 times 10 to the third eV, and after all that you get about 0.0529 nanometers, or about 0.5 angstroms, where remember an angstrom is 1/10 of a nanometer. Okay, so this is the value of the Bohr radius, and what it tells you is that if we for the ground state of hydrogen, where z equals 1 and n equals 1, then what we expect is that the orbital radius for the ground state is just equal to the Bohr radius, and so it gives you an estimate of the size of the ground state of the hydrogen atom, the actual physical size of the atom, and it's equal to about, the radius is equal to about half an angstrom. So the diameter of the ground state of hydrogen atom is approximately equal to an angstrom, okay, or 1/10 of a nanometer.